Hi, I'm Andrei Kozyrev, and today I would like to tell you about our paper called RocqStar. We've been working on it in a team with Nikita Khramov, Gleb Solovyov, and Anton Podkopayev at JetBrains Research. Since recently LLMs are used more and more to generate code, but let's take a closer look at what programmer does when using an LLM. First, one specifies the expected output of the model, and when the result is received, one should check whether it meets the specification. On an example of a simple request to GPT, I formulate my request in plain English and retrieve results. Now my goal is to check whether the generated code does what I requested. In this case, it's very simple, so we can quickly make sure that everything is fine. However, when the generated code grows, checking that it coincides with the specification is not trivial anymore. Sometimes this code would look really unfamiliar, and even unit testing may not be sufficient to determine correctness when, for example, concurrency is involved. The question is whether we can reliably check the correctness of the generated programs. And the answer is yes, through formal verification. Back to our example, how would we define a sorting algorithm? Well, basically it is something that takes a list of natural numbers as an input and returns a sorted permutation of this list as an output. Such specification is very precise and unambiguous. If we have any function that coincides with it, it will be a correct sorting function. Formal verification allows you to automatically check the implementation against such specification. One of the existing means of formal verification is called Rocq. There are more of them, but this work focuses on Rocq. To write a sorting function in Rocq, one would formulate a theorem called sort, which will assume you have a list of natural numbers, and you need to prove that there exists such permutation of this list that its elements are sorted. If you have a proof of existence of such permutation, it is going to be the same as having an implementation of a sorting function. Rocq allows you to formulate a theorem, write a proof for it, and the system will handle the rest, ensuring that the proof is correct. Proofs are constructed from elementary building blocks called tactics, which continuously modify the proof state. If you have it complete, as seen on the slide on the left, Roqq's system allows you to use the proof, and in this scenario to sort a list of natural numbers. You can see a sorted list in the window on the right, and the implementation of the resulting sorting function could be afterwards extracted into OCaml or other languages. Now I would like to present you our work called RocqStar. High-level objective of the work is improving how an AI agent generates Rocq code. Our contributions include a novel approach to doing retrieval for Rocq theorems, as well as a multi-agentic system interacting with Roqq's MCP. The first contribution is BigRocq. It's a tool used to augment a dataset of Rocq theorems. BigRocq takes a proven theorem and presents its proof as a tree, where nodes are different proof states and edges are tactics used in the proof sequence. Each subtree is actually a standalone substatement with its corresponding proof. That process allows us to expand the dataset of theorems by roughly a factor of 4. The central contribution of the paper is a novel approach to perform premise retrieval for Rocq. When an AI agent generates the proof for the target theorem, it benefits from seeing other statements proven in a similar manner. Existing work does premise retrieval by utilizing syntactical statement similarity as a proxy to proof similarity. However, we show that this is suboptimal. Let's consider an example of those two theorems. If we assess their similarity only based on their statements, we will deduce that these theorems are not really relevant to each other. From the other side, if we take a look at their proofs, they are similar both semantically and syntactically. Using our dataset of Rocq theorems, additionally post-processed using BigRocq, we train an embedder that, given two statements, estimates how similar their proofs are. The retrieval serves as a core component in our pipeline. In addition to it, we develop a multi-agentic system tailored to Rocq generation. Given a target theorem and a set of premises extracted from the same file or project, we process them by our trained encoder model. Afterwards, k-most relevant are chosen according to the cosine similarity between embeddings. Accompanied by the plan produced throughout a multi-agentic debate, they are passed to the executor component. Executor continuously explores the Rocq proof environment and composes the proof. A reflection component is activated when the executor is stuck to enforce context exploration and retrieval. We evaluate both components of our approach and achieve promising results. RocqStar retrieval component outperforms both baselines and supports the claim that retrieval in Rocq could not solely rely on statement similarity. RocqStar agentic system also shows significant improvement over existing baselines, especially on harder theorems. And that was basically it. I thank everyone for the interest in our work, and I'm happy to chat on the conference and per email. Bye.